everyone. Today I'm going to talk about this simulation of vibrational emission spectrum for low temperature plasma. Here we combine the QDB and the Exocross. Yeah. So yes. So first, I will give a brief introduction, just to talk about why we simulate this spectrum for plasma, especially low temperature plasma. Then I will talk about the method we use, including QDB, this Quantemol, the global model for plasma chemistry, data, this lifetime database, and the Exocross. And then I will talk about my results about the species distribution, emission spectrum. Finally, I will draw some general conclusions. So why we study plasma chemistry? Because plasma is a very important tool for almost all the industry activity, such as this semiconductor fabrication. People use this plasma enhanced CVD to do the etching for semiconductor fabrication. Also, plasma can be used to fabricate this waterproof or oil-proof surface. Also, in this automobile industry, people use a lot plasma technologies. On the other hand, by contrast, we don't have universal comprehensive modeling for the dynamics of chemistry in plasma. This is the reason why we want to model this plasma chemistry, especially the dynamical process. So here is the example for the another reason is the complicated nature for the plasma chemistry. Basically, you have many species involved in the chemistry, and also have many reactions. So the method is a Quantemol database for species and reactions. You can see here we have the reaction for CO2. This is the interaction, the reaction, we can say, between the electron and the CO2 and so on, some other heavy particle inflation reactions, and also integrated in this QDB software. We have this global model for Python. Global model realized in Python. So essentially, this Quantemol, the global model, is to solve a series of differential equations to figure out this dynamics for electron density, for example, and this heavy particle density, and so on. Yeah, the thing we are interested in this model is this heavy particle density. Yeah, so we can figure out this distribution of the heavy particles, and then we can just do the we can compute the emission spectrum. Another important component in our simulation is lifetime of the species, because these species, especially the excited state, not staying there forever. It will decay to the ground state. This is an important process. So the data for the lifetime or the decay rates, it takes this data from the lifetime database. This you can find this in this Exomol website. So another very important step in our simulation is to use this so-called Exocross to compute the emission spectrum. And here's the formula, and here's the data. Yeah, we can just combine this or integrate. We can say integrate this data. For example, the degeneracy or this the matrix elements between the final state and initial state to compute the emission spectrum. So the whole process is this. We include the decay of the vibrational excited state up to five vibrational excited states in our Quantemol global model simulation, and then we add this heavy particle calculation for vibrational excited state using the data in the so-called stellar database, the reference data here. We integrate this data and essentially the decay and inflation reaction into this global model, and then obtain this species distribution. According to this distribution, then we compute this emission spectra using this pi Exocross. Is the realization of Exocross in Python, developed by Jinxin in our group. So here are the results. We have this CO2 distribution. You can say this we compute the species essentially density. We can also say distribution, okay, according to different pressure. Okay, yeah, you can say higher pressure because this CO is very dominant. CO weight equal 1. Yeah, that's the distribution. And then we can just use this distribution, we can compute the emission spectrum. Yeah, for example, we have the emission spectrum for this one, CO weight equal 1. Then we just combine this population into our emission spectrum calculation. This has been implemented by Jinxin. Yeah. So, and also, yeah, this is the detailed distribution. We use this distribution for our following calculation of the emission spectrum here. And so far, we have do the 10-part simulation. We can say this is the emission spectrum based on this distribution. Yeah, you can imagine if we have different distribution, we can have this different emission spectrum. And then we can see the clear peak from CO and the CO2. Yeah, and this one CO. So far we have done some simulation for CO2 with this higher pressure, 100 par and so on. We found that the CO spectrum is completely dominant compared with the CO2 emission spectrum. So we show the spectrum of CO only here. Yeah. So yeah, so by conclusion, so we have induced the emission spectrum by integrating QDB, LiDAR, Quantemol, and the Exocross. We obtain species distribution, and we can clearly see the emission spectrum of CO2 and CO in this normally this low pressure. We can say low pressure and ambient condition, room temperature. Yeah. Yes. So in the following, finish the spectrum calculation for CO2 and population, and also we can extend this methodology to other interesting systems such as this N2 plus O2, this nitrogen gas and the oxygen gas. Another thing is we can also transform the software, the whole process into a single Python software framework. This will much more efficient if we want to compute the emission spectrum of plasma according to this plasma chemistry simulation. Yeah, so that's it for my talk. Here I thank Jinxin in our group, Professor Jonathan Tennyson, Dr. Sabah Chenmo from Quantemol, Alec and Martin. Yeah, thank you very much. And also many thanks for the funding from this, from especially ICIC. Yeah, and I take many. Yeah, I learn a lot from this Exocross website. Yeah, please visit this website. Yeah. Okay, so thank you for listening. Yeah, here for the question. Yeah, thank you.